I'm going to talk to you more about the hyperbola standard form. And as we saw in class, this is the hyperbola standard form. You can kind of recognize it because it's got x and y in it on the left side. It's got a minus sign between the x and the y. It's got squareds on both the x and the y. On the right side, it's got a 1. And dividing the x squared and the y squared, you have squares underneath in the denominators. Okay, so those are the characteristics, several characteristics which make it a hyperbola formula. But I would say the most important characteristics are the x squared, the y squared, the minus. Those are the most important ones. Okay. Now, what does the 4 and the 3 mean here? Okay. Now, as we saw in our investigation, the 4 and the 3 are related to the x and the y. And so, for example, the 4 is underneath the x, so it's related to the x. The 3 is underneath the y, so it's related to the y. These are transformations. And the transformations that the 4 and the 3 are doing are kind of like stretch compressions. Of course, the 4 is doing a horizontal stretch compression because it's underneath the x. And the 3 is doing a vertical stretch compression because it's underneath the y. Okay, so let's see what that looks like. There's something kind of neat about hyperbolas in that when they do the stretch compression, they form a rectangle in between the two sides of the hyperbola. So as we saw in the investigation, these hyperbolas kind of are like diagonal hyperbolas. They're not like the rational functions that we saw before, the reciprocal functions that we've seen up until now. They're reciprocal functions that are kind of rotated. And if you look at this orange rectangle here, you can see that this orange rectangle has a width of 8, or from 0 to 4, and from 0 to -4. And it's got a height of 6, or it goes from 0 to 3 and 0 to -3. So do you see how the values that we had underneath the x and the y, which were 4 and 3, determine the size of this orange rectangle? Okay, and do you see how this orange rectangle is the frame for the purple asymptotes? Do you see how the asymptotes cross through the corners of the rectangle? So once you draw the orange rectangle using the values 4 and 3, you can see how that already gives you the asymptotes also. Okay, so from the 4 and the 3, we've determined the orange rectangle, which tells us where the vertices are. The vertices are going to be here and here, right? And it also tells us the purple asymptotes, which kind of, that pretty much between the vertex and the asymptotes, you pretty much know what the hyperbola looks like. It looks like that, right? Now, what is the 0.5, 0, and -5, 0? These are the foci, or the two, focuses that were used to generate the hyperbola if you look at it from the point of view of what we call conic sections, which is our next chapter. Okay? So in the investigation, this was the little moon that we were trying to go between the moon and the planet. Okay? So the basic two steps are you draw the orange triangle, or the orange rectangle, so that you know where the vertices are and what the slope of the asymptotes are, and then you just draw the hyperbola so that it follows along the asymptote, but then goes through the vertex and then follows along the asymptote again. Now, one more thing about the equations. There is a variation which you might see. And that variation is that on the right side, instead of seeing a positive 1, you might see a -1. And the reason why you might see a -1 is because this is kind of like a sideways hyperbola. So let's see how that works. If you have a -1 on the right side, how could we make it so that there was a positive 1 on the right side? Well, what you would do is you would multiply the whole thing by negative 1. So you'd multiply this by negative 1, multiply this by negative 1, multiply this by negative 1. And so what we would get is we would get negative x squared over 4 squared plus y squared over 3 squared equals 1, right? And then once you rearrange that so that the positive term is in front, you end up with y squared divided by 3 squared minus x squared divided by 4 squared. So we reverse the order, right? Now, when you reverse the order, you can imagine that if you reverse x's and y's, you are actually creating a sideways hyperbola because you're kind of turning it, you're changing the x with the y, right? You're kind of doing like a variable interchange. So let's see what happens. I'm going to take this function here. I'm going to put a negative 1 here instead and see what happens. Oh, look what happened. We now have a hyperbola is turned on its side. And do you see how now instead of the vertices on these left and right sides of the orange rectangle, we now have vertices on the top and the bottom of the orange rectangle. Okay, and actually the focus or the foci of these this set of hyperbolas is also going to be 5 away from the 0 point, but instead of being 5, 0, it's going to be 0, 5 and 0, negative 5. Okay, they're not drawn here. So isn't that interesting? Just by changing the right side to negative 1, we kind of flip it so that instead of it's on the left side and right side, it's going to be the top and the bottom. Okay, similar to when we had the reciprocal function, if we had a negative m value, it inverted the quadrants where the hyperbola was going to be present. Okay, and remember that if you make the right side negative 1, it's the same thing as keeping the right side positive 1, but making the left side y squared minus x squared instead of x squared minus y squared, right? If I wanted to look at the equations for the asymptote, you can see that since the orange triangle has a height of 3 and a rise of 3 and a run of 4, you can imagine that the equation for the for this asymptote would be y equals 3/4 x, rise over run, right? And then this opposite asymptote would be y equals negative 3/4 x because it's a similar slope, but it's going down instead, right? Okay, let's go back real quick to the equations. Okay, so we just talked about this blue one here. And now let's go down and talk a little bit about translations, okay? So when you work with hyperbolas, you can also do translations of the hyperbola, horizontal and vertical translations. So what does that look like? Well, let's go back to our very first transformation, which is the quadratic, okay? And remember, all this time we've been learning transformations, we've always had that inconsistency where when we look at the h value and the k value, the h is a little bit different than the k because the h has a negative here or a minus here and the k has a plus. Remember that? We've always had to like say, okay, if it's x minus h, the actual value for the center of the vertex is going to be the h itself, not negative h. And then the plus k, the k is going to be the y value of the vertex or the center. Now, if we rearrange this, we could move the k to the left side, and it'll turn out to be y minus k on the left side and x minus h on the right side, right? And then it looks a little bit more similar, right? The y minus the k and the x minus h, those are kind of written similarly with a subtraction, right? Now, the reason why I show you that is because if you look at the transformation or the translations horizontal and vertical for the hyperbola, it looks like that, where you have an x minus h inside the parentheses squared, and you have a y minus k inside the parentheses squared, okay? So since in this equation we don't have the form where we have y on the left and everything else on the right side like we've been doing up until now, it's pretty hard to do that with the hyperbola. That's why they don't do it, okay? Because it's arranged a little bit differently, there's not really an advantage to putting y by itself on the left. So now we can put it in its, most consistent form, where the x has the h subtracted from it and the y has the ak subtracted from it. They both look very similar, right? So looking at this, we could say that the h and the k kind of represent a center value for the hyperbola. We'll call it the center of the hyperbola, and we'll say it's h comma k. Now, the center of the hyperbola is not the vertex. Let's take a look at the picture of the hyperbola once again. So like this would be the center value, and you can see at the center of the hyperbola there's really nothing there, right? It's the center of our orange square or rectangle. It is where the asymptotes intersect, but the hyperbola itself is this red curve, and the red curve does not go through the center. So we do have what we call vertexes or vertices of the hyperbola. Those are the 2 points on the orange rectangle that the hyperbola goes through and touches kind of in their center. But the center of the hyperbola would actually be this point here. And when you have an untranslated hyperbola, that would be at 0, 0, but when you translate it, let's try to translate. Let's translate it to like 2, 1 or something, okay? So I'm going to put x minus 2 and then I'm going to put, and then I'm going to put y minus 1 here. Y minus 1. Okay? And then you can see that I have now translated the red hyperbola set 2 units to the right, 2 units to the right, and 1 unit up. And that's what happened here. The h value is 2, the y value, the k value is 1, and so therefore I've translated both vertices 2 to the right and 1 up. 2 to the right and 1 up. Okay, and the same thing would happen with the orange rectangle. You could also consider it translated the exact same way, and the purple asymptotes, you can also consider them translated in the exact same way also. Okay, and that's it.